In this session, we will talk about coupled material and energy balances in heterogeneous catalytic reaction systems. Okay, so this will be useful for Q4 of your coursework. So also for Q3, but you should be able to do Q3 without this. Okay, so let's jump into it. And if at any point there is anything unclear, feel free to interrupt me and ask your question. Yeah, so I can only see my slides on my screen and I won't be able to see if your hand is raised on Teams. So if you have a question, you have to speak up. Okay, you have to unmute your mic and speak up and just interrupt me. That's okay. Okay, so at the end of this lecture, you will know the steps involved in a heterogeneous catalysis. Okay, you will also know the difference between internal and external mass transfer resistances. Yeah, and you will understand concept, yeah, effectiveness factor, and how to use it to analyze heterogeneous catalytic reaction systems. Okay, so as you know, heterogeneous systems mean that there is more than one phase involved. Okay, more than one phase involved. So for heterogeneous catalytic reaction systems, in many cases, you will have your reactants and or products either in the gas phase or in the liquid phase or in both phases. Yeah, and your catalysts will be typically in the solid phase. Okay, so you will have a solid phase and a gas phase, or solid phase and a liquid phase, or if you have a three-phase system, for example, a slurry reactor, then you will have your solid phase, and then you'll also have your liquid and gaseous phases. Okay, so you have a solid phase for your catalyst and fluid phase. So when we say fluid phase, it's either the liquid phase or the gaseous phase. Yeah, fluid phase, it's for your reactants and for your products. And solid phase for your catalyst. Okay, so I hope that's clear. And finally, we will derive a heterogeneous model for a catalytic converter. Okay, so let's start off by reviewing some of the types of catalytic reactor. So one common type of catalytic reactor is the packed bed reactor. Okay, so most of which use porous catalyst particles, so porous catalyst particles, to get the greatest surface area per unit volume of bed. Okay, so using a packed bed increases the contact between the two phases, so between the fluid and the solid phase, compared with other reactor types, because in packed bed, the particles are as close together as possible. So most packed bed reactors are of a cylindrical design with either random packing, so you have pellets and other shapes, as you can see in this picture here. Or you can also have a structured bed, okay? Structured bed. So for example, a monolith. Have a mono, so from its name, okay, so mono, so your catalyst is just one whole piece. Yeah, usually with a honeycomb structure to maximize the surface area. So you can see one at the back of the picture. So here, yeah, that is a monolith. So it's just one big piece of catalyst sitting inside your reactor. Okay, and you can see, hopefully you can see the honeycomb structure there as well, although it's a little bit small. Okay, so a common example is the catalyst in catalytic converters in vehicles. Catalytic converters in vehicles, that is a monolith. Okay, so that converts unreacted hydrocarbons and carbon monoxide to water and carbon dioxide, which are less harmful substances. So we can breathe a bit less polluted air in cities. Okay, so another type of reactor is the fluidized bed. Okay, so here catalyst pellets are suspended by the upward flow of gas or liquid. Okay, so that the bed behaves like a liquid rather than a solid. Okay, that's why it's called fluidized bed. So we will just mention it here in this module because you will learn more about it in your final year when you take the advanced chemical engineering module. Teach the catalytic processes of that unit. So we will meet again after this term and talk about catalytic reactors like fluidized types of reactors. Okay, so this is a close-up of a region in the catalyst bed. So this part here is a closed-up of a region in the catalyst bed. And then here, this one, it is zooming in on a single catalyst pellet. Yeah. So here you can see the stagnant film around a single catalyst. Okay, you should have learned stagnant film theory from your previous modules. So we will use stagnant film to stagnant film theory to model external mass transfer or external fusion. This one, okay, so this picture here, it shows in more detail the pellet and the fact that the catalyst pellet is porous. Okay, so you can see the pore channel here. So inside the pore channels, we have internal mass transfer or internal diffusion. Okay, so you have your bulk phase, yeah, surrounding the catalyst pellets. So you have your fluid flow here. Yeah, but they're also here, so they're surrounding. Your bulk phase is surrounding your catalyst pellets. So in order for the reactants, so the reactants are in the fluid phase, yeah, in the bulk phase. So in order for the reactants to reach the active site of a catalyst. So remember that in catalytic processes, the reaction takes place only on the surface of the catalyst. Okay, so the reaction takes place on the solid phase. Okay, so very little or no reaction takes place in the bulk phase. Okay, all of the reactions takes place. It takes place inside your pellet. So your reactants, they need to reach the surface of the catalyst pellets. So they need to migrate from the bulk phase, yeah, into the pellet. Inside the pellet, it needs to travel inside the pellet as well, okay, to reach the active sites. Okay, so once they are in the active sites, then the reaction can take place. And um, that happens in several steps. Okay, so the migration of the reactant from the bulk phase to the active site, that requires a number of steps. Okay, so let's look at the steps. So first, the reactant will have to diffuse from the bulk phase. Okay, so here, this is your stagnant film. So the boundary of the stagnant film, that is at the bulk phase concentration as well. So this is at bulk phase concentration. Okay, so your reactant have to diffuse from the bulk to the surface of the catalyst pellets. Okay, so this is known as external diffusion. Okay, so from stagnant film theory, we can assume that all external diffusion takes place just in the stagnant film. Okay, all external diffusion takes place here in the stagnant film. So we can easily model it. Yeah. So the properties in the bulk are all uniform. Okay. But here in the stagnant film, okay, so the concentration of the reactant decreases, okay, from the bulk phase concentration to the surface concentration of the catalyst pellet. Okay, so the concentration here is higher than the concentration here. Why is that? Yeah, because there is a resistance associated with external diffusion. Okay, there is a resistance associated with external diffusion, and we call that external mass transfer resistance. Yeah, if you can remember how to model mass transfer resistance, yeah, so when you write your rate, the rate is equal to the driving force divided by the resistance. Yeah, so your reactant need to overcome that resistance. Okay, but we know that the resistance that's just an inverse of the mass transfer coefficient. Yeah, so if we know the mass transfer coefficient in this film, then we know the resistance that the reactant needs to overcome to cross this, yeah, from the bulk to the surface of the catalyst. Okay, and we know how to calculate mass transfer coefficients, right? So Kc, we know how to calculate that. So we have correlations. So you can remember the Sherwood number. Yeah, Sherwood number, that's in terms of Kc. Yeah, there's a Kc there in the Sherwood number. So you can use that. More generally, there are correlations like the Fruchtling correlation or Satterfield correlation. So you can use that to calculate Kc. And then 1 over Kc times the area, external area of your, so this one, of external area of the catalyst pellets. So that is your mass transfer coefficient for diffusion, external diffusion. And then the inverse of that, that's the external mass transfer resistance. Okay, so we are here now. So your reactant traveled from the bulk to the surface. And once it has reached the bulk, um, your reactant needs to diffuse inside the pores of the catalyst pellet through the pore channels. Okay, so you have pore channels here. And that is known as internal diffusion, yeah, or internal mass transfer. And there is another resistance associated with, so your concentration, the concentration of your reactant will drop from the surface um, to the center of the pellets. Okay, it needs to overcome that resistance to internal diffusion so it can diffuse inside. Okay, and how do we model that internal diffusion? So inside the pore, there can only be diffusion there, yeah, because the pore, it's very narrow. Okay, it's very small, that there is no bulk phase in there, so we don't have any convection inside the pore, because convection is due to the movement of the bulk phase, and we don't have the bulk phase inside the pore, so we only have diffusion inside the pore. And then there are many mechanisms for diffusion, yeah. So um, you have your molecular diffusion, so collision between particles, yeah, between molecules, between species when they collide with each other. So that's molecular diffusion. Your species can hit the wall, so they can collide with the wall, and that's called Knudsen diffusion. Yeah, there's also surface diffusion. So you have many active sites here along the pore channel, along the wall of your pore channel, and your species, when they get attached to an active site, they can also migrate to another active site depending on the concentration difference. So that's called surface diffusion. So there are many types of diffusion. So we capture that, so different types of diffusion, using our effective diffusivity. Okay, so the effective diffusivity, that takes into account as well of the fact that your pore channels may be of irregular shape and size. Yeah, so that takes into account of the tortuosity, because the pore channel may not be a straight line, or most likely it will not be straight. And you also have the pore constriction. So pore constriction, that's the ratio of the smallest to largest diameter. Okay, but you should know this. You know what effective diffusivity is, and then we can just model internal diffusion using Fick's law. Okay, and then at any point inside the pores of the pellets, as I've said, so in the channel, pore channel, the wall of the pore channel, there are active sites in there. Okay, so at any point inside the pore of the pellet, or even on the external surface of the pellet itself, yeah, the species or your reactant may encounter an active site of the catalyst, and then when it encounters an active site, it will then react. Yeah, so your reactant will be converted to your product. Okay, so again, note that the reaction only takes place on the catalyst active sites. Yeah, the reaction only takes place on the catalyst active sites. Very little or no reaction is taking place in the bulk phase. Okay, so this is just a different view. So this is our solid phase, which is the catalyst pellet. So here you can see the pore channels where internal diffusion is happening. So next to the external surface of the pellets, we have our stagnant film. Okay, this is our stagnant film. And using this theory, stagnant film theory, we will assume that all of our external diffusion is just taking place here. Okay, there's no diffusion in the bulk phase. So uniform property throughout the bulk phase. Okay, so here A is our reactant and B is the product. Okay, so let's see what's taking place. So the different steps. Okay, so this is step one. So step one, the reactants have to diffuse to the surface of the pellet from the bulk phase. And this is known as external mass transfer. Okay, and then step two. Okay, so step two, the reactant then have to diffuse through the pores. Okay, and this is known as internal diffusion. Okay, and then step three. Okay, so at any point in the pores, the species can react on the catalyst surface. Okay, so in this lecture, we will just treat this reaction as a single step. Okay, so step three, reaction on an active site on a pore wall. Yeah, but in the advanced chemical reaction engineering module, we will break this down into further steps. But here, we will keep it relatively simple. Okay, just a single step reaction. Okay, so now your reactant is converted to product B. Okay, and then step four. Okay, so the product then have to diffuse. Okay, the product then have to diffuse out to the surface of the pellets. So this is internal diffusion again. Yeah, internal diffusion again. So now your product is on the surface of the pellet. So last step. So step five. So the product needs to diffuse out, okay, from the surface of the pellet into the bulk fluid. Okay, so your product needs to reach the bulk fluid again. So there will be another external diffusion. Okay, so step five is external mass transfer. Okay, so let's model them. So you have 5 steps and you already know how to write the rate of each of these 5 steps from your earlier modules. Yeah. So let's revise. So for steps 1 and 5, so steps 1 and 5, these are external diffusion steps. So we can use the stagnant film theory. So again, if you can remember, that involves a mass transfer coefficient. Yeah, mass transfer coefficient Kc. So we can write the flux of A to the surface of the pellet. We will denote the flux as Na. So this is equal to the mass transfer coefficient Kc multiplied by the driving force. Okay, so the driving force is the bulk concentration, CAB, minus the surface concentration, okay, or the concentration of A at the surface of the pellets. Okay, so if you write it for A, this is for the flux of the reactant. But you can also write one for step 5, okay, for the product. Just replace A with B. Okay? Okay, so steps 2 and 4. Steps 2 and 4 are internal diffusion steps. Yeah, so these are inside the pore. So we said that we can use Fick's law to obtain the flux of the reactant into the pores and the product out of the pores. Okay, so Fick's law states that the flux, so again, flux of A, we'll denote as Na. This is just the effective diffusivity, yeah, multiplied by the concentration gradient along the radius of the pellets. Okay, so here you can see that, yeah, the concentration changes along the radius of the pellets. Okay, we said that before, that the concentration drops, okay, from the surface of the pellets to the center of the pellet. So we have a concentration profile along the radial direction in the pellets. Okay, so the minus sign here is because diffusion occurs from high concentration to low concentration. Okay, so you should know this sign here. Okay, and then step 3 is just a typical reaction at the conditions at a particular point inside the pellets. Okay, so here we wrote it for a first order reaction. So again, I would like to emphasize that Ca, concentration of A, is a function of the radial position in the pellets. So write it this way, Ca of R. Okay, so we have all of the rates. Okay, so now I want to introduce the effectiveness factor. Okay, this is everything is old. Okay, you have learned everything. The ones that in my previous slides, all of that you have learned from your previous module. So this is the only new thing here, the effectiveness factor. Yeah. So um, I will introduce this by considering this seemingly counterintuitive example. So I'll give you a minute to read the text on the slide, and then I will explain. Okay. So if we have a heterogeneous catalytic process, then you would expect the reaction rate to be proportional to the area of the catalyst available. So double the area and you will double the rate of reaction. So assuming excess reactants, yeah, if you have plenty of reactants. So if we use larger catalyst pellets, then there is more surface area for the reaction. Okay, but in some cases, the rate of reaction can actually decrease instead of increase. So how can this be? Okay, so the reason for this is that the larger particles means that there is a larger distance for the reactants to diffuse inside to reach all of the active sites. Okay, so if the rate of internal diffusion is lower than the rate of the surface reaction and the external diffusion, then the internal diffusion will be the rate determining step of the overall process. Okay, so here we have several processes taking place. Yeah, so we have external diffusion, we have internal diffusion, and we have the reaction. And the rate determining step is the rate of the slowest step. Okay, and if the rates of internal diffusion is lower than the rates of surface reaction external diffusion. If you use a larger particle, it means that there's actually a longer distance, okay, larger distance for the reactants to diffuse inside to reach all of the active sites. Okay, so in some cases, you may not have enough supply of reactants into the site because your surface reaction is faster than internal diffusion. So the concentration of reactants inside the pore will get depleted. Okay, so you will observe some slowing down of your reaction. Okay, so the reactant concentration in the pores will drop rapidly as it's consumed faster than it can diffuse inside the pellets. So if you average the rate of reaction over the whole pellet, you'll find that it's less than the rate at the surface. Okay, so this effect is characterized by the effectiveness factor. Okay, the effectiveness factor is defined as the total rate of reaction over the whole pellet. Okay, this is divided by the rate of reaction if the concentration inside the pore channels was the same as the surface of the pellets. Okay, in other words, it's the rate of reaction with no diffusion limitation, okay, or with no resistance to internal mass transfer. Okay, what do we mean by that? So if there's no resistance to internal diffusion, what will happen? Okay, so if there is a resistance to internal diffusion, we expect the concentration of A to drop from the surface to the center, yeah, because of that resistance. But if there's no resistance to internal diffusion, then your reactant can diffuse easily inside the pore. okay, without any problem. So the concentration inside the pore channel will be the same as the concentration at the surface. Okay, so that's just the definition of effectiveness factor, which we will denote as eta. This is the actual or the overall reaction rate in the pellet divided by the reaction rate at surface conditions, okay, at surface concentration. Okay, it's like an efficiency. Okay, efficiency, that's your actual rate divided by the ideal rate, okay, the maximum rate, because the maximum rate takes place when um, the concentration of reactants inside your pore is the same as the surface concentration. So that's the maximum rate that you can get. So this is just like an efficiency. Okay, so if you know the value of the effectiveness factor, if you know eta, the effectiveness factor, then you can just consider the reaction rate at the surface concentration using the methods that you have learned before on how to write reaction rate expressions. Okay, so you can write this RAS, but remember that this is at the surface of the catalyst. Yeah, but same method as how you would write rate expression before. And then you can just multiply that by the effectiveness factor eta. Okay, and eta, effectiveness factor, that will handle the effects due to internal diffusion and reaction. Okay, the internal diffusion effects are in here, as well as the surface reaction effects. So for example, if you have a first order reaction like this one, so RAS, negative RAS is a first order reaction. So we can write it as K1 CAS. Okay, remembering, so the subscript S here is because this rate is at the surface of the catalyst. Yeah, this is surface rate. So we use surface concentration. Okay, so again, remember that the reaction only takes place on the solid phase or the surface of the catalyst or the active site of the catalyst. Okay, so when you can write this, so you can easily write that, so you know how to write rates expression. You can just multiply that by the effectiveness factor eta, okay, to get the overall rate of your catalytic process. So easy, right? So you need this. You need this guy, the overall rate of reaction for your material balance. Yeah, because for the material balance for the reactor, you have accumulation. Okay, so the same one that we use is general material balance or general energy balance. Okay, so the general balance is accumulation equal to in minus out plus plus generation. Okay, and you need this in the generation term. Okay, so the material balance for the reactor will be the same, but in the generation term, you will have to use the overall rate of reaction, meaning you will have to use the effectiveness factor times the rate at the surface concentration. Okay, so I hope that everything is clear so far. Any question? Okay, you have to speak up because I can only see my slide. I can't see Teams. I won't be able to see if your hand is raised. Okay, so if you have any question, just interrupt me. Yeah? Okay, I haven't heard anything, so we will move on. So as a case study, we will look at a catalytic converter. Catalytic converter. Catalytic converters remove harmful gases from vehicle exhausts. Okay, so in particular, the main reactions for petrol vehicles are shown here. Okay, so catalytic converters convert carbon monoxide, nitrogen dioxide, and hydrocarbons, yeah, into less harmful compounds like CO2, nitrogen, and water. Okay, so this is what a typical catalytic converter looks like. Okay, so it is based on a monolith support. Okay, so it has a monolith support with catalyst coating, uh, coating the walls of the cell. So you have a cell here. Yeah, so in our picture, that was a honeycomb structure, but here, to simplify things, it's just a square cell. Okay. So, and you have catalyst coating here on the wall of your cells. Yeah, so you have a lot of cells here. You have cells here, here are your cell units. Yeah, and here we're showing just one cell, and you have catalyst coating here on the wall of your cell. Okay, and the catalyst coating is porous. Okay, so there is a high surface area of catalyst. Yeah. So this one is showing the the catalyst wall or the monolith wall and the catalyst coating. Okay, so the wall, the monolith wall, and the catalyst coating. Okay, so looking at the monolith in detail, in more detail, schematically, so you can see that there is a repeating cell, yeah? And this is a repeated cell. So our schematic here shows a repeated cell. So again, you have the wall. So that's the blue region. Okay, the blue pattern. That's your wall. And that is the monolith supports. Yeah, and it is covered by the catalyst coating. So the region that is shaded, or the red pattern here, that's the catalyst coating. So most of the area is void. Yeah, most of the area in your monolith is void for the gas to flow through. So you have low pressure drops. Yeah. So the different phenomena that occur in your monolith in the reactor are shown on the right. Yeah. So the different phenomena. So here we have the bulk gas flow. Okay. And between the gas phase and the catalyst coating, you have convection, yeah, of heat and convection of mass. Okay, so we can have convection here between the gas phase and the catalyst coating. You can have convection. And then inside the catalyst coating, so here you have your catalyst coating. You will have what? You will have your catalytic reaction there. And you'll also have conduction of heat. Okay, so remember those phenomena because those are the things that we are going to model. Yeah, so here, bulk gas, between the bulk gas and the catalyst coating, we have convection, both mass and heat convection. Yeah, and then in the catalyst coating, we have the catalytic reaction and conduction of heat. And we are going to use the effectiveness factor, yeah, eta, to describe the effect of internal diffusion. So here I did not indicate internal diffusion, but there is internal diffusion taking place, but I don't indicate it here, yeah? Because we will use eta, we will multiply the rate of reaction by eta, so that is taken account into that. Okay, so the effectiveness factor, which we will use later to multiply with the rate of reaction, that will handle the effects due to internal diffusion. Okay, so we're only showing reaction here, but there is actually internal diffusion taking place. Okay, is that clear? We're only showing the reaction here because we will use the effectiveness factor eta to take into account of the internal diffusion effects. Okay, and don't forget you have conduction of heat as well on the wall. Okay, so that's clear. Okay, so this is what a real monolith looks like. Okay, so the close up, so this is the real monolith. You can see the large number of cells, and then we have a close up here. Okay, we have a close up of the cells, and you can see here a number of modeling challenges. Okay, modeling challenges. Yeah, but we will use some simplifications. So what are the modeling challenges that you can see? Okay, so you can see that the catalyst coating, okay, is not uniform. Okay, so for example, you can see the build up on the corners. Yeah, there's build up on the corners. And this could create temperature hotspots. Okay, and also the thick layer in the corners, means that internal diffusion resistance becomes important. So the thicker your catalyst coating becomes, okay, the higher the internal diffusion resistance is. Yes, that makes sense, right? Internal diffusion becomes more important the thicker your coating is. Yeah, and here we can see that in the corner, the catalyst coating is thicker. Okay, but we will just make some assumptions. Okay, so this is reality. Modeling is an idealization. So we will just assume that the reactors are well insulated and there was a good or uniform flow distribution to all of the channels. Okay, so that means that we can only that it's okay to model just a single channel. Okay, so we will just model a single channel. Okay. So again, here is our monolith. And this is a close-up of the wall and the catalyst coating. So looking in more detail, you can see the bulk phase at the top. Okay, so this is the more detailed representation. So this is our bulk phase, and this is the stagnant film. So you can see the bulk phase on the top and then the stagnant film next to the catalyst coating. And then inside the catalyst coating are the pore channels. Okay, and then in the pore walls, those are where the active sites are. So let's quickly have a look at our steps. So we have external diffusion from the bulk phase to the catalyst coating surface. And then there will be internal diffusion of the reactants into the pores, and then you will have reaction. And then once the product is formed, it needs to internally diffuse out to the surface, and then it needs to go back. Okay, the product needs to travel from the surface to the bulk phase. Okay, so 5 steps. So just to remind you, these are the same steps we described before. We wrote the rate expressions for each step. Yeah, we have the rate expressions for each step. Okay, so that's great. So for this case study, we will focus on one of the reactions. Okay, we will only consider one of the reactions. So the reactions that we will consider is the one that converts carbon monoxide to carbon dioxide. Okay, so you know from your previous modules and our past lectures how to write a general reaction model. So it will be easy to extend this model to include other species and reactions. Okay, so note that this reaction rate expression is in terms of the surface area of the catalyst. Yeah, so note that the units are mole per square meter of catalyst surface per second. So where normally, so typically, we write the rate in terms of it's per cubic meter of reaction mixture, or per cubic meter per volume, per unit volume of the reactor. So we need to be careful in our mass and energy balances because we have a different units for the rates, for the rate expression. Yeah, so each unit in the balance, so if it's material balance, it's mole per second. And if it's energy balance, each term has units of joule per second or watts. Yeah. Also note that this reaction, this rate expression is at surface concentration. Surface concentration. So because the reaction only takes place at the solid phase, at the surface of the catalyst. So that's why we denoted this with subscript S. Yeah, so we have in the concentration as well. These are surface concentrations. Okay, so we want to develop a model that can predict the temperature and concentration profiles in both the gas and catalyst coating phases. Okay, so remembering our systematic approach to model building, the first step is to draw a sketch of the system and the control volume. Okay, so this is a rough sketch for now, but we will make more detailed ones and annotate them when we write the material and energy balances. Okay, so this is the monolith. Okay, from a different view. This is seen from the side with the channel running left to right. Okay, so let me see. I made a, okay, it's here. So imagine this, yeah? So imagine that this is your monolith, and this is the view that we've seen earlier. So imagine that there are several cells here. Yeah, that's the view we've seen. So now we're looking at this view. Yeah, we're looking at this view. So the channel running left to right. Yeah, so this is our inlet here. Okay, I hope you can see it. I'm not sure if you can see it. Yeah, so before that's the view, and we have many channels here on this view. Yeah, and then in this schematic, we're just looking at this at the side. Yeah, seen from the side. Okay, and then below is a magnified view of one channel. Okay, we will only model one channel because we made an assumption earlier that allowed us to model just one channel. Okay, and then we will label the coordinates. Okay, so we will take the gas inlet as Z equal to 0. Gas inlet is Z equal to 0. And then the outlet as Z equal to L. Okay, so again, this is our single channel. This is a single channel. This is our gas phase here. Gas phase. Okay, and this is the solid phase. So the region shaded green, yeah, that's our solid phase. And the solid phase is composed of the solid wall and the catalyst. Okay, so our assumptions. So we need to write down our assumptions. That's the next step. So first, we just want to write a steady state model. So we will leave out the accumulation term in our balances. And then remembering the picture of the whole monolith, we will assume the flow distribution is good or uniform, and that the catalytic converter is well insulated so that we can only consider a single channel. Okay, we'll only model a single channel. Assumptions 3 and 4, we will assume plug flow and perfect mixing in the radial direction. So our model will just be a one-dimensional model. Okay, so our model will just be a distributed model along the axial direction. Okay, we'll just model it as a function of Z. Okay, okay, so our model is going to be distributed in the Z direction only. Assumption 5, we will also assume a high enough gas velocity to neglect axial diffusion or dispersion. So we will only consider convection. Okay, and then assumption 6, as mentioned before, we will use an effectiveness factor to describe the effect of internal mass transfer resistance in the catalyst coating. And then assumption 7, we will neglect any reactions in the gas phase. Okay, there are likely to be much smaller than the catalyzed ones taking place in the catalyst coating. So it is safe to neglect the reactions occurring in the gas phase. Okay, so the fun part. Okay, so let's start with the CO balance for the gas phase. So let's start with the CO balance for the gas phase. So as always, we draw our control volume. So this is our control volume. So this is just for the gas phase, yeah? So this is at axial position Z and with the length delta Z. It only includes the gas phase. And then we mark all of the fluxes into and out of the control volume in the diagram, yeah? So fluxes in and out. Okay, and then we write the general dynamic material balance. And then we remove all of the terms allowable by our assumptions. Okay, so steady state assumption. So assumption 1, steady state, means we don't need the accumulation term. Assumption 7, no reaction in the gas phase, means that we don't need the generation term. Okay, so now we just have fluxes in and out of the control volume. So we have here NCO at Z. See, this is the flux going in. And then we have NCO Z plus delta Z. This is going out. So this and that, okay, are in the axial direction. Okay, so going in and out of the control volume in the axial direction. Okay, so here we just write that. Okay, NCOZ, this is going in and this is minus going out. In the axial direction, we will have to multiply this by the area because this is a flux, yeah? And the area that we will take is the area normal to that, okay? And that is AC. We will denote that as AC, okay? Area proportional, area normal to the flow in the axial direction. Okay, and then we have another, and then there is another flux of CO going from the gas phase to the solid surface, yeah? From the gas phase to the solid surface. So NCO, gas to solid. And we will denote this as, yeah, NCO GS to indicate that this is the flux from the gas to the solid phase. So for this flux, so this is the flux here, so minus because it's going out of our control volume. So we will need to multiply it by a different area, yeah? And that area is AS because the direction of flow is different. This is in the radial direction, yeah? This here are in the axial direction. So we'll denote that area as AS. So note that the fluxes, so these fluxes are different from this flux. So one is axial and the other is radial flux. So remember what we did last week for heat transfer? We also had axial conduction, axial conduction and radial heat loss. So before we did it with energy, and here we are doing it with mass or moles of species, but the principle is the same, yeah? So these fluxes are in the axial direction, and this one is in the radial direction. Okay, so let's now define the two areas, AC and AS. Okay, so because the cross section is not circular, we will describe this non-circular cross section of the channel using hydraulic diameter. Okay, hydraulic diameter is defined as the diameter of a circular cross section that gives the same hydraulic behavior as the non-circular duct or channel. Yeah, so you can look up how to calculate hydraulic diameter for different shapes. But here we will just denote this as D subscript H. Okay, so hydraulic diameter, DH. I'm sure you will have learned what hydraulic diameter is from your previous modules. Yeah, you should know this from your previous modules. Okay, so now we've defined hydraulic diameter. So we can just now use a circular cross section to describe our channel using the hydraulic diameter to give the same behavior as the non-circular channel. So this cross section, the cross sectional area AC is therefore, okay, so this cross sectional area here, this is just pi dh squared over 4. Yeah, agree? Okay, so this one, the one that is normal to the axial flow. So using the hydraulic diameter, we can just assume that this is circular. Yeah, so the AC is this, and then the one that is normal to the one that is normal to the flow from the gas to the solid. Okay, so we can write this as pi dh. Yeah, so it's as if you have a cylindrical channel. Yeah, and you know how to write a cylindrical channel. We had that, it's not a channel, but cylindrical tube, cylindrical rod last week. Yeah, so you know how to write AC and AS for a cylindrical rod. Yes, it's just pi dh. There's the circumference of your, well, cylinder. It's cylinder now because we're using the hydraulic diameter times the thickness of your control volume. Okay, so again, this is very similar to what we have done for cylindrical system, for which we had several examples in the lectures. Okay, the first line here is the equation as we had on the last slide. Okay, this is the same equation on the last slide. And in the next line, we just substituted in the definitions of the areas. Okay, so we just substituted in the expressions for AC here, and then the expression for AS here. And then we divide through by AC delta Z, or divide through by pi dh squared times delta Z over 4. Yeah, and then take the limit as delta Z goes to 0. Okay, so there's nothing new. We've done this many times now. So you should be very familiar by now with how to convert your control volume balance to a differential equation. Okay, so this gives us the differential equation here. Okay, so finally, we just need to substitute in the expression for the fluxes. Yeah, we have NCO here and we have NCOGS here. So let's do it first for NCO. So this is the flux in the axial direction. Okay, so we write the axial flux of NCO in the can be due to diffusion or dispersion. Okay, so this is how you model diffusion or dispersion. Okay, and then you can also have contribution from convection as shown here. Okay, so this is the dispersion or diffusion term. Okay, so for those of you who ask how to model this dispersion, yeah, here it is. Yeah, this is how you model dispersion. You should know this already anyway from your previous modules. Yeah, and this is the convection term. So, however, we assume that there will be no axial dispersion or diffusion. Okay, so remember one of our assumptions 3 and 5. We assumed no axial dispersion or diffusion. So, which is a reasonable assumption if the flow rate is high enough. So, the flux of CO is just the velocity of the gas times the concentration of CO. Yeah, so the velocity times the concentration is the convective flux. okay, which you should already be familiar with. Okay, so the flux is just due to convection. We just substitute this into here, and we get this here. Okay, assuming that the velocity is constant. So we take it out of the derivative. Okay, and then we need to define this as well, the flux from the gas phase to the solid phase. Okay, so how do we do that? Okay, so this is just, okay, so if you go back here, this is that one, yeah, towards the catalyst coating. And we will use our stagnant film theory. Yeah, so we will write the mass transfer, external mass transfer in stagnant film. So we wrote that earlier when we looked at the 5 steps. Yeah, and that is just equal. So this one NCO. So flux of CO from the gas phase to the solid phase. That's just equal to Kc times the driving force. Okay, so concentration of CO in the gas phase minus the concentration of CO in the solid phase. Yeah, so this is just the external mass transfer in the stagnant film. Okay, that's just that NCO. We just wrote this out like this. Okay. Okay, so any question? So we've derived the concentration profile in the gas phase, concentration profile of CO in the gas phase. Okay, this is our first differential equation, and this is a first order equation, first order differential equation. So we need one boundary condition. And the boundary condition, we can take that at the inlet. Okay, so at the inlet, at Z equal to 0, the concentration is the inlet concentration. Okay, CCO comma 0. Okay, so we're not done yet. We've just started. That's our first differential equation. Remember, we're modeling heterogeneous systems. So we have a gas phase and a solid phase. So let's do the solid phase for now. Okay, so solid phase. Okay, this is the CO balance for the solid phase. So our control volume now is over the solid parts only. Okay, so this is our control volume now. This is indicated by this red rectangle here. That's our control volume. Actually, this is this one, yeah. So it's not two, it's one whole piece. This is a side view, and this is the front view. Yeah, so this is our control volume. The green pattern here, that's our control volume. Okay, so we write, this is for the solid phase, so we write the same general material balance. Okay, this is general material balance, and then apply simplifying assumptions. So assumption 1, steady state. So we can drop the accumulation term. Okay, so now we have to be careful with the units of the reaction rate. Okay, so we have a generation term here in the solid phase. Yeah, we have to be careful with the units of the reaction rates. We take the reaction rates as defined at the surface concentration. Yeah, so I told you to remember this guy, RCOS. Yeah, so which is in mole per square meter of catalyst surface per second. So this is at the surface concentration. So we need to multiply it by the effectiveness factor. So here we just defined it, yeah? So this is the rate at the surface concentration. We multiply it by the effectiveness factor eta. So this term here, eta times this rate at the surface concentration, that is our overall rates. Yeah, but we have to be careful with the units. Okay, so we multiply it by the appropriate volume. Okay, appropriate volume and the surface of the catalyst area per unit volume, okay, which we will denote as AP. Okay, so AP, that's the surface area to volume ratio, and the unit is this, yeah? So square meters catalyst per cubic meter of the bed. Okay, and the volume here, that's this one, volume. Okay, so I'll explain this volume here. So if we assume, so this is our control volume again. So this is one cell, yeah? So we have the gas phase here. This is the solid phase. And if we assume that the thickness of the catalyst coating, yeah, of the catalyst layer here is much smaller than the diameter of the channel. So this is much smaller than the diameter of the channel. Then we can take the volume to be AC. So this is AC is the cross-sectional area of the gas phase, yeah? Gas phase channel, AC, times the thickness of our control volume, times the length of our control volume. So we can just define V, okay? volume of the bed or volume of a single channel. We're just doing it for one channel. This is just AC times dz. Okay, so I hope that's clear. Yeah. So just be careful with the units. So this guy here is per unit area. So we multiply it by the surface area to volume ratio. This is area per volume. And then we'll multiply it by the volume of the bed. Okay. So this is the equation from the last slide. And we just replace, in the next line, we just replaced AS with pi dH delta Z and the volume by AC times delta Z, and AC is pi dH squared over 4. Yeah. And then next is to divide each term by pi dH squared over 4 delta Z. And delta Z will cancel out. Yes, it will cancel out. This is equal to 0. Okay, and then substitute in the flux for um, the flux of CO from the gas to the solid phase. So we wrote this previously. We wrote this previously for the flux of CO from the gas phase to the solid phase. And then finally, okay, so we write that. So that's it's this one. So NCOGS is just this Kc times the concentration at the bulk phase or the gas phase minus the concentration at the surface. Okay, and then okay, so I'm aware of the time. So if you have another commitment, so feel free to leave the meeting. I'm recording this, so I will carry on and I will complete this complete discussing the rest of the slides, and then I will upload the entire slide. Okay, the entire recording to our Moodle page. So if you have other commitment, because it's a 4:15 now, so just feel free to leave the meeting. Okay, so we'll carry on. Okay, so we substituted, we wrote this before, and we just substituted that expression, okay, that we wrote before here. And then finally, we just substitute in the rate expression. Okay, so we just defined this now, RCOS, and that was a given, yeah, in the problem statement. So we are given that RCOS is just equal to Kr, and the concentration of CO at the surface and the concentration of oxygen at the surface. So you just substitute that into here, and we'll get this. Okay, so we have now our second differential equation. So this is the differential equation for the CO in the solid phase, yeah, in the solid phase. Okay, so the next thing to do is the energy balance, because we need our temperature profile. Okay, so let's now do the energy, the gas phase temperature as a function of Z. So let's start again with the gas phase. So our control volume again is the control volume that we used when we did the material balance for the gas phase. Here it is. Okay, so as always, start with the general dynamic energy balance. Okay, start with the general dynamic energy balance and start applying assumptions. Okay, so assumption 1, it's a steady state. So we can drop the accumulation term. And then there is no reaction in the gas phase, assumption 7. So drop the generation term. So, and then we just have the fluxes, yeah? So the energy coming in, or the heat coming in to the control volume, is the heat flux, QZ. So this is in the axial direction, okay, multiplied by the cross-sectional area AC. Okay, so AC is the normal to the flow in the axial direction. Okay, and then this one is the flux leaving the control volume. So it's the same thing. So flux leaving the control volume, so you have the negative sign here, and then multiplied by the cross-sectional area. Okay, and then we also have another heat flux there, so going out of our control volume. So that's from the gas phase to the solid phase. Yeah, and we need to multiply it by the area normal to that flow, which is AS. Okay, so flux times the area. Okay, next step. So this is the same equation as in the last slide. And in the next line, we just substituted in the expression for AC. Yeah, AC here, and then AS. This is AS. Okay, and then we divide by pi dH squared over 4 delta Z, and then take the limit as delta Z tends to 0 to get a differential equation. Okay, so we'll get this dq by dz. Okay, and then we're not done yet because we want the temperature profile. Okay, and Q depends on the temperature, so we need to define this in terms of the temperature. So this is the heat flux in the axial direction. Yeah, so this heat flux is due to conduction dispersion. Okay, so this is the conduction dispersion term. So again, here is your friend dispersion, in case you're wondering how to model dispersion. Okay, so in this example, we will drop the dispersion term because of our assumption, no actual dispersion or conduction. But you may need it somewhere else, yeah? Hint, hint. Okay, and we have the convection term here. Okay, so here our flux is just due to convection. So we only have this term here. So we just substitute that in. So Q is equal to the convection term, yeah? Substitute that into here. And then assume that the velocity, density, and molar heat capacity are all constant, so you can take them out of the derivative. So you'll have this term here. Okay? And then finally, the heat flux, this guy here, Q, the heat flux from the gas phase to the solid phase. Okay, QGS is just the heat transfer coefficient, H. So this is taking place again, yeah? Taking place at that stagnant film, yeah? So if you look at your control volume here, there's a stagnant film here, okay? And we will write that, that flux, okay, from the gas to the solid in that stagnant film, yeah? This is a stagnant film theory, so that's the heat transfer coefficient H times the driving force, yeah, which is the temperature of the gas phase minus the temperature of the solid phase. Okay, so again, this heat transfer is taking place in the stagnant film next to the external surface of our catalyst coating. Okay, so we substitute that in here. Yeah, that's what we did here. And we get our final differential equation for the gas phase temperature. Okay, so this is a first order differential equation. So we need one boundary condition. And that boundary condition is at the inlet condition. Okay, so the temperature at Z equal to 0 is the inlet temperature. Okay, so we're not quite finished yet because we need to calculate the solid temperature Ts. Okay, this guy here. This is the solid temperature, and this also varies along the axial direction. Okay, this varies along the axial direction. There's a temperature profile as well for this in the axial direction. So the last thing to do is to write the solid energy balance. Okay, this is the energy balance for the solid phase. So for the solid wall, we will use the same control volume. Okay, so here, this is the side view, this is the front view. This is our control volume here. Okay, so we have conduction in the axial direction in the catalyst. So this is conduction. And the wall, yeah? So this solid phase here, that's the catalyst coating and the wall. So QZ coming into our control volume and QZ plus delta Z going out of the control volume. So we also have convection from the gas phase to the solid phase. Yeah, convection from the gas phase to the solid phase. Yeah, so this is QGS. Yeah, so it's the same thing as the previous energy balance for the gas phase. And now we also have a generation term because we are now doing it for the solid phase, and there is reaction taking place in the solid phase. Okay, so we have Qgen here in our balance. So our general energy balance looks like this. And we can cancel the accumulation term as we have done previously because it's a steady state. And then this leaves the energy flows in and out of the control volume and the generation term. Okay, so the energy flowing into the solid from the gas phase. So this guy here, from the gas phase to the solid, yeah, QGS, as we defined it in the gas phase, but it's now going into our control volume. So solid phase, yeah, this is our control volume. This guy now is going into, so previously in the gas phase balance, it is going out of the control volume. But now it is going into the control volume, because our control volume now is in the solid phase. So this is going into, so it has a positive sign. Oops, where is that? Yeah, this one. It has now a positive sign. So it's an incoming heat flow. Okay. Okay, so, and then we have the QZ and QZ plus delta Z. They are conduction heat flows. Okay, they are conduction heat flows. And then we have the generation term. So this is the same term from the material balance. Okay, so this bit here, same term as in the material balance, but now we multiply it by the heat of reaction. Okay, so recall that for an exothermic reaction, the heat of reaction is negative. So we have a minus sign here. Okay, since you want the generation term to be positive, you want this whole term here to be positive, since the reaction is adding heat to the system. Okay, so for exothermic reaction, it's adding heat to the system. So you want this generation term here to be positive. That's why we put a negative sign here, because delta HR is negative. Okay, so maybe you have noticed this. So this ACS here. Okay, so the area that we multiply with the conduction flux. So this is different from the one we used before. Yeah, for the material balance, for the solid phase. This is different because it needs to be the cross-sectional area of the solid. Okay, cross-sectional area of the solid, not the gas phase. So before we used the gas phase. Okay, but now it needs to be the cross-sectional area of the gas phase because the conduction is taking place in the solid. Okay. Okay, so here we denoted this as ACS. So it's ACS here. And again, this is the blue part of this diagram. Okay, not the white part. The white part is for the gas phase. Okay, so how do we get ACS? Okay, so this area here, this shaded region here, how do we get that? Okay, so we can use this definition. Okay, to get ACS, we use this definition. Okay, so 1 minus the bed voidage. So bed voidage, that's the fraction of the empty space in the bed. Okay, so 1 minus the bed voidage. That's the fraction of the solid part in the bed, yeah? Solid part of the bed. This is 1 minus the void in the bed. This is equal to, okay, so the fraction of the total area of the solid, ACS, yeah, divided by AC plus ACS, okay, divided by the area, okay, of the gas phase plus the area of the solid phase, okay? But we can assume that the catalyst coating is thin, yeah, and this is a small, very much smaller compared to the diameter of the gas channel. Okay, so if you assume that the thickness of the catalyst coating is thin, then in the denominator, we can say that this is significantly smaller than AC. So my denominator will just be AC. Okay, so we can have 1 minus the bed voidage is approximately ACS over AC. So we can use this to get an expression for ACS. So here, ACS, okay, is just equal to 1 minus the bed voidage times AC. We wrote AC before. Yeah, AC is this. That's just the cross-sectional area of the gas phase channel. And then we wrote volume as well before. So we need volume here. So volume is the same as before. Yeah, AC times the thickness of our control volume. Okay, we're getting there, almost there. Okay, so substituting in the area, substituting in ACS into here and the volume into here, we will get this expression here. Okay, and then we divide by pi dH squared over 4 times delta Z. Okay, and then we substitute in the expression that we have for QGS. We have this flux before. Yeah, we wrote that before. And then we take the limit as delta Z tends to 0. Okay, and then we will get this differential equation. Okay, so we have dq over dz here. Okay, and then the final step is to define q. Okay, because this q is a function of temperature, so we need to write it out in terms of the temperature. Okay, so this is due to conduction. Yeah, this is in the solid phase. This is due to conduction, so we can use Fourier's law. Okay, so Fourier's law, this one. This is Fourier's law for conduction. Okay, and the conduction is in the axial direction in the solid phase. Yeah, this is Fourier's law, only conduction in solid. So we just substitute that into here. Okay, and then we take the K out of the derivative. We assume that the thermal conductivity is constant. And then you'll get this. Okay, so this is our temperature profile, or the temperature of the solid temperature, profile of the temperature of the solid along the axial direction. Okay, that is our last differential equation. But don't forget the boundary conditions. So this is a second order differential equation. So we need two boundary conditions. Okay, so this is the final step for the solid phase energy balance. We define our boundary conditions. So it is a second order differential equation. We need two boundary conditions. So there are two sets of possible boundary conditions, and I'm showing it here. Okay, so the first set is that the reactor is insulated at both ends. Okay, so thus the temperature gradient is set to 0 at Z equal to 0 and Z equal to L. Okay, so insulated at both ends. Temperature gradient is 0. Okay, so this is another set. Okay, so this other set is that the heat flux at either end is determined by heat losses to the external environment. Okay, so heat flux or heat losses or heat flux at either end, okay, at either end is determined by the heat losses to the external environment. You should remember this because I discussed with you the various boundary conditions that you can have for a wall. Okay, so revised topic 4, heat transfer boundary value problems. Okay, if you can remember, I discussed there the different boundary conditions that you can have for a wall. Okay, so we've derived our four differential equations with the boundary conditions. Okay, so those are all of the equations we need. So in summary, in this lecture, we discussed the different steps in a catalytic reaction process, and we defined the effectiveness factor. We wrote down the rates for the different steps in a catalytic reaction. And finally, we developed a heterogeneous model for a monolith catalytic converter. Okay, so we developed the model by formulating the material and energy balances for the gas phase and solid phase. And from the material and energy balances, we derived a system of differential equations describing the concentration and temperature profiles along the axial direction.